kick off. So good morning, everyone, and thank you for joining us at this Discovery Round 3 phase show and tell webinar. This one's all about supporting networks to drive the decarbonisation of heat. We'll be hearing from a few projects looking in that space. So next slide, please. So I'm Joe Davidson, and I'm one of the project managers and internal monitoring officers on the Ofgem Strategic Innovation Fund at Innovate UK, and I'll be introducing and hosting the Q&A sessions for 5 of our projects in our current round 3 discovery phase. And I'll give you a brief overview of the SIF first of all, and some of our key highlights to date. Next slide, please. So the Ofgem Strategic Innovation Fund is part of a 5-year partnership between Ofgem and Innovate UK, part of UK Research Innovation. And it's all about delivering energy network innovation with the vision of accelerating the UK's transition to net zero at the lowest cost to consumers. And it's also about making the UK the best place for an energy business to grow and scale, overall making the UK the global hub for energy innovation. As part of this, through our purpose, we have 3 main groups of people, planet and business, that we're looking to deliver benefits for, which you can see on the slide. Cost reduction, new products and services, and active alignment for people, carbon reductions, energy security and risk and resilience for planet, and then innovative energy system, growth and finance investment for businesses. So next slide, please. And as part of this, how we deliver this is a part of our mission. So we have 6 key elements to this, and this helps us to achieve that vision and fulfill our purpose that I highlighted in the last slide. So we issue 4 annual innovation challenges across 3 stages of funding: Discovery, Alpha and Beta, which you can see highlighted on the right-hand side of this slide here. With Discovery looking at feasibility studies, Alpha being proof of concept, and then Beta being full demonstrations. And across this, we have a focus on alignment, diversification of the pipeline, ensuring responsiveness, and supporting commercialization, which in turn allows the Ofgem Strategic Innovation Fund to fund truly transformational projects, generating an incredible amount of evidence and insights, some of which we'll be hearing about in the rest of this session. Next slide, please. And in terms of some of the key highlights to date, through our first 3 rounds and our funding opportunities, to date we've supported 201 projects and awarded over £136 million in funding. And as an early indication of benefits generated by these innovations, we see an impressive potential cost saving of more than £2.6 billion out to 2035. And we're just halfway through the programme with our round 4 challenges launching earlier this year. And as part of that round 4 ideation phase currently. Next slide, please. So for round 3 discovery, we had 53 applications being awarded funding. And today's show and tell is all about demonstrating what has been achieved by projects in the supporting networks to drive the decarbonisation of heat space. So just some context on this area, why it's so important. So as the GB energy system transitions to encompass that net zero future, we're moving from a system of dispatchable energy generation, providing a firm, flexible power system, to one of greater intermittency, of inverter-based generation, such as wind power. Decarbonising the production of heat in this context of the system is not only a challenge in its own right, but its integration into energy networks also provides some further challenges. However, there's also a number of potential opportunities around flexibility to better support networks, for instance, in helping to make that transition to this new energy system. And to support these challenges and enable timely heat decarbonisation, better coordination and visibility are needed for local heat requirements against network constraints. And this will then help better inform network planning activities alongside increasing accessibility of flexibility solutions and markets to support peak demand, whilst meeting the needs of all consumers, especially the fuel poor and vulnerable. And in addition, where flexibility options have been exhausted and reinforcement must be pursued, further action is required to ensure that fair and equitable circulation of reinforcement costs to avoid households and businesses which may adopt technologies later being disadvantaged due to factors such as socioeconomic status, poor housing stock, and/or network status. And next slide, please. So as you can see from our agenda, we have 5 projects presenting in this session. we'll have a short break around 5 to 12. We'll get 5 to 10 minutes to stretch your legs, and then we'll come back for the last two presentations. So from each of the 5 projects, we'll have a 5-minute presentation and then a 5-minute Q&A. If you do have questions, please type them in the Q&A box and we'll look to pick them up in the space after the presentations. And on that note, let's get started. So the first project we'll be hearing from is OptiHeat. So I'll hand over to the UK Power Networks and the rest of the team to get started.
Yeah, thanks very much. My name is Rob Davies. I'm from UK Power Networks, and I'm here to present with the OptiHeat project. Next slide, please. And next. So the aim of the project is we'd like to develop a tool to help domestic customers determine what the most cost-efficient investment will be in terms of a correctly sized heat pump for their property, paired with different insulation measures and other low-carbon technologies. The project has several project partners, including the University of Sheffield, EDF Research and Development, the University of Sheffield Sustainability Centre, and South Yorkshire's Community Foundation. This project is building on a previous project called the Catalyst project between University of Sheffield and EDF, which was developing a tool to help determine what the most cost-efficient heat pump would be for properties. Next slide, please. So what's the problem we're trying to solve? What we found is that people, even if they want to try and decarbonize their homes, in general, they just don't know what they should be spending their money on. The cause of this is that it's very complex. There's many types of LCTs, different sizes, different flavors they can consider, and they don't know which ones are best for them. Also, cost is a major barrier. LCT is very expensive to install, and the running costs can be quite unclear. There's also a lack of simple tools. There are tools out there to help determine the optimal sizing of specific LCTs, but they don't take a holistic view across multiple technologies. We know this is a challenge for many parts of society, so it includes homeowners, but also local authorities, landlords, and vulnerable customers, who we think are particularly impacted by this due to, of course, their kind of lack of funds or potential lack of digital skills. One finding we saw from the previous Catalyst project was that LCT installers are also tending to oversize equipment for people's homes. That's a problem for DNOs because it means there's going to be higher peak electrical demand, which means we'll have to reinforce early or unnecessarily to meet that capacity. Next slide, please. So what's our solution? We call it OptiHeat, and it's a digital tool which would take inputs from the customer, for example, information about their house, so how many rooms it has, the EPC rating, maybe even what type of radiators they have. The tool will then run an optimization considering the costs of these devices, the running costs, and other things like grants available, as well as tariffs. And then the tool will run this optimization, produce an output and a recommendation for these customers on what they should be investing in. Next slide, please. I'd like to pass to Alec from EDF.
So now that we have the kind of the general form of the solution, this part of the discovery project looked at actually the specific cases which it can be applied, and and how that fits in to the stakeholders. So we engaged a range of stakeholders, and we came up with a long list of use cases for this tool. Can we go to the next slide, please? And then what we did is we refined and developed the use cases. We evaluated them and we down selected them, and we've come up with a list of 5 use cases that fit into three categories that we want to move forward with and develop further in an alpha project. Next slide, please. So I think I'm passing on to Jane.
Thanks, Alec. We undertook a knowledge review to identify the drivers and the barriers for investment in low carbon technologies. We use these findings to inform the use case selection that Alec's just been talking about and refine the tool design. Unsurprisingly, we found that high upfront costs, were identified as a significant barrier. as was the uncertainty around potential cost savings. Conversely, good knowledge and awareness of low carbon technologies is a significant driver, particularly when communicated via householders, own social networks, and via tradespeople. The crucial thing, though, is that a number of factors work in combination, and these factors also change with time. For example, a house move can initiate investments in low carbon technologies. The knowledge review also informed a stakeholder engagement plan, which has been designed to implement participatory ideals such as inclusivity and accessibility. We use these learnings to inform our stakeholder analysis, methods of engagement, and the phased approach which Adam will take you through now.
Next slide, please. A phased approach was proposed to enable participants to reflect on and develop stakeholder contributions. So this table summarizes that. Engagement will be undertaken in phases by applying different methods of engagement, which is on the right-hand side, in the hopes to select different stakeholders. We also developed purpose-based question categories with the overall intention to support the narrowing down of the use case selection, increasingly detailed design of the use cases and move, and enable reflective contributions from participants over time, which was as prescribed in participatory ideals and best practice. Next slide, and passing on to Darren.
Thank you. So in a previous project that Rob mentioned called Catalyst, we developed a simple app that would enable customers to very quickly evaluate the viability of installing a heat pump for their property. And that's indicated in this left flow chart. The flow chart on the right describes the software architecture of an extension to this workflow, where we support the multi-objective optimization of the trinity of investments in upgrades to the fabric of a property, the substitution of a heating system, but also the installation of renewable energy technologies, specifically photovoltaic panels. Next, please. So this is an example. So the chart that you see here is an example of the optimization process, where we have one objective, which is the capital cost of a bundle of renovation measures on the x-axis, and on the y-axis we've got the energy demands that results from that, the uptake of that bundle of renovation measures. Each of the kind of purple dots, or the connected purple dots, represents what we call a Pareto front of non-dominated solutions. So that's the combination of renovation measures for a particular capital cost that returns the best energy performance. And we can see that that ranges from positive energy demands to negative energy demands, where our property is a net exporter of energy to the grid. Next, please. So now we see a similar kind of result. But now we've got an alternative second objective function, which is our energy cost savings relative to our original base case description of an archetypal semi-detached dwelling. So as we move to progressively increased capital costs on the x-axis, we see that we have different alternatives of improvement to the insulation of the fabric of a property, the substitution of a heating system, and at the higher costs, also the integration of photovoltaic panels. At a certain point, so around £28,000, we see that there's a big increase in energy cost savings, because now we've paired batteries with heat pump and PV installations, so that now, rather than exporting energy to the grid at a relatively low tariff, we're avoiding future imports from the grid at a higher tariff, so that we've got correspondingly greater energy savings, because we're storing energy in a battery for future use. And that's it. Next, please. Thank you.
Thanks very much. So that's the tool, but why do we want to do this? What's the benefits of this? For customers and society, what we think is that customers are going to be able to save money, primarily. So by giving them what the most cost-efficient investment is going to be, we've calculated that on average, customers could save about £156 per year on their running costs. We're also giving people more knowledge. So this tool is going to give kind of a holistic view and recommendations of what technologies to invest in in hopefully a trustworthy way. We're also going to help save CO2 from getting emitted to the environment. Less energy being consumed obviously means that less energy needs to be produced. For UKPN, we can also help support fuel poor customers, again, by giving them kind of very specific bespoke advice. But we can also take greater consideration of things like what grants are available to them. We also should be able to save money on reinforcement costs. We've calculated that on average, there's about a 0.7 kilowatt saving per property, utilizing a greater range of insulation measures, which as you scale up could result in some strong capacity reinforcement prevention. There's also some operational improvements as well through the use of not having to reinforce some customers' domestic capacity. And finally, through getting a better visibility of what LCTs are on the network, we can improve our load forecasting as well. Next slide, please. So what's next for Alpha? We want to kind of push things forward in all of these areas. From the multi-objective optimization side of things, we want to expand, so we're looking at a greater number of technology as well as different housing archetypes, but crucially, how we can develop this so it can really come out at scale. In terms of the digital tool, we also need to define kind of what that tool would look like, the user interface and kind of the back-end processes as well, and develop a prototype to help show people during our customer engagement. We also want to further evaluate and validate our use cases that we've defined so far. For that, we want to carry out the stakeholder engagement plan that we've defined, but also complete some market analysis and develop and refine our CBA for the use cases. And finally, we want to look at the route to market. The crucial questions really are, who should pay for this tool, who should own this tool, and how do you fund it? And then we also want to look at kind of what UKPN commercial products kind of fit into that as well. And that's everything. We're happy to answer any questions.
Awesome. Thanks very much, guys. We've had a couple of questions come in the chat. So first one, could you give a bit more information on how the tool is different to other tools out there already in existence?
Yeah, I can have a first go and happy for anyone in the team to contribute as well. So from what we've seen from tools out there, a lot of them either only look at one specific type of LCT at a time when they're trying to size it, whereas this is taking a more holistic view. What we've also seen is there are tools which do take a more holistic view, but they really are not a user-friendly tool. It requires kind of some sort of technical knowledge and know how to use it and kind of quite detailed work to actually get the outputs you need, or kind of some specific software required. So this is kind of more user-friendly tool that customers can actually interact with. I'd say it should also consider a number of other things. So it's not just about domestic customers' costs, but also reducing peak electrical demand. This should be able to also take account of that as well. Anyone else in the team, happy to, if you want to contribute as well.
We're getting quite a few questions in the chat. I think we'll have to pick some of these up typed in the chat afterwards. So we'll do one or two more maybe. You mentioned it slightly in the plans for Alpha bit of different stakeholders and who's involved in what, but is there a view on who will market the tool to customers? Is it on networks, energy suppliers, local authorities?
Yeah, so that's a crucial part of the Alpha phase plan, is to kind of take that evaluation, because we see there's several options. It could be the DNO owns it, it could be the supplier owns it, it could be, you know, maybe someone who's considered more trustworthy in the industry, like a net zero charity, for example. So a crucial part of the Alpha phase scope is to kind of evaluate those different options and, you know, to help answer that question really.
Awesome. Then one last one. We've got, how will this work with the heat loss survey that the installers will use to determine the sizing of the heat pump? Do you see renewable energy companies who install heat pumps, solar PV, etc., for homeowners as your main customer?
I think possibly Darren or Alec might have a better answer than me on this one.
Sorry, I didn't quite catch the question. Would you mind repeating it?
Yeah, how will this work with the heat loss survey that the installers will use to determine the sizing of the heat pump? Do you see renewable energy companies who install heat pumps, solar PV, etc., for homeowners as your main customer?
Okay, so in the heat pump ready program project that preceded this, we developed a workflow that was compliant with the MCS processes. So we've got an MCS compliant calculation methodology, and similarly, so we're still working on the development of a method that would enable customers to video capture the layout of their property and to add attributes to a 3D description of their property to speed up the more detailed analysis of the specific kind of sizing and configuration of a heat pump installation for their property. So we've done what we can to automate the process and to reduce the number of visits to a property, if that makes sense.
Awesome, thanks so much. I think we have to leave it there for the questions, but if some of the project team can pick up typed answers to those that are outstanding, that would be great. Thanks very much for those submitting questions. Do continue to do that throughout the rest of the presentation. Next slide, please. Yeah, so we've got CoolDown next. So I can invite the Electricity Northwest and team to turn their cameras on and run us through their presentation.
Good morning. Next slide, please. Yeah, that's on. Good morning, everyone. I'm Delroy Ainsworth, Innovation Project Manager at Electricity Northwest. And this morning, I'm going to be going through the CoolDown project, which we did in partnership with Guidehouse and UCLC. And representing those partners will be Callum Coughlin from Guidehouse and Ollie Smith from UCLC. Next slide, please. So, as Britain warms due to climate change, electrification of heat will mean increasing customer access to space cooling, leading to increased summer peak demands. In distribution network planning, cooling demand is currently poorly accounted for and based on limited high-level modelling. Additionally, cooling's potential to provide flexibility during periods of network stress has not been considered. CoolDown aims to explore the impact of cooling on network capacity by producing improved uptake and demand projections, as well as developing novel commercial models to incentivise and unlock space cooling flexibility, reducing network reinforcement requirements and optimising value for customers. So in a nutshell, the main purpose of the project is to better understand cooling demand on the distribution network. And then once equipped with this better understanding, we will then look at the potential of managing the increased demand with network flexibility. So some of the things we currently know about AC are that 10% of UK electricity is already attributed to air conditioning. 65% of office spaces and 30% of retail spaces currently have AC, and more than 30% of English homes are at risk of overheating in the future. And there'll be a 7 gigawatt increase, or up to a 7 gigawatt increase in the UK-wide summer peak loads in a 32% AC adoption rate scenario. One important thing to highlight is that there's a real lack of clarity on network impact of increased space cooling, and this was something the project was looking to address. And how we did that can be broken down into the 5 key steps listed at the bottom of the slides, where we modelled future cooling uptake, explored cooling impact on the network, performed cost-benefit analysis, evaluated cooling DR, and long-list DR commercial models. And as we go through the presentation, we'll talk about these in more detail. Next slide, please. Hand over to Ollie for this one.
Thank you. Well, the objective of the work package here at UCL was to look at 2 representative substations, one rural and one more urban, and to model the predicted increase in cooling at those 2 substation sites, and also to evaluate what the resulting increase in power demand would be, and would demand side response be able to mitigate that increase at those 2 sites. The methodology that we used to do this was based around building physics modeling. So roughly what we did, and I have to skip over this quite quickly, is we looked at the 2 substations. So one of them was the substation that serves the centre of Chorley. The other was the substation that serves a village in Lancashire called Rawsonstall. We then identified which buildings are served by those 2 substations. We then pulled together data from various different sources, Ordnance Survey, Energy Performance Certificate data, Valuation Office data, to build up a representation of each of these buildings. And then, in a sort of hand-wavy way that I don't really have time to go into, we plugged that data into a building physics simulation engine, Energy Plus, that can simulate internal temperatures and the power demand, the power load from the building's cooling and heating equipment. And what we did is we looked at these two different substations for two different points in the future, 2030 and 2050, evaluated how many of those buildings at each substation would experience overheating. And then we used that as a basis for determining which buildings would actually choose to acquire air conditioning. So buildings that were simulated to overheat would get air conditioning. And what we found is that between 2023 and 2050, you go from 0 out of 46 buildings overheating in the Chorley area to 16 out of 46 overheating. And it's even worse in the more rural area, where you go from 23 buildings out of 121 needing overheating to 80 buildings needing, to 80 buildings experiencing overheating. Next slide, please. So then what we did is we took those buildings that were experiencing overheating and equipped them in our simulations with cooling equipment to bring their internal temperatures down to a more comfortable level. On the left two panels, you can see the time series over a year for the cooling load at the more domestic substation. So that's for Chorley. And you can see that when we apply demand side response, so that's by changing the set point when there's an increase in the load, we actually reduce the cooling load by 26% without actually introducing any additional overheating. And it's a similar story for the Rawtenstall substation, where by introducing demand side response, so that is again increasing the cooling set points, we can reduce peak cooling load by 45%. And again, that doesn't introduce any overheating. So demand side response is quite effective at these two areas for bringing down peak demand without causing discomfort. Next slide, please. Dal?
Yeah, I'll pick this one up. So, excuse me. Yeah, so we took the demand figures from the UCLC model and then added them to our baseline forecasts. So that's the forecasted uptake of EV and heat pumps from our DFES, and then the AC from the UCLC modelling. We then extrapolated across two full primary substations to better understand the potential impact of cooling on the network, identifying the need for reinforcement with and without DR. Those two primary substations consisted of 36 distribution substations, so the numbers you can see on the graphs are out of a total of 36. 4 scenarios shown on the graphs are max cooling, which assumes all overheated buildings install SC, max cooling with DR, which assumes all overheated buildings install SC and customers participate in a DR program, 50% cooling, which assumes 50% of overheated buildings install SC, and 50% cooling with DR, which assumes 50% of overheated buildings install SC and customers participate in a DR program. So looking at the top graph, max cooling uptake shows that 9 of the 36 substations exceeded capacity by 2030 and 26 of the 36 by 2050. Using DR, deferred reinforcement on 2 substations by 2030 and 1 by 2050. For the 50% cooling uptake, 2 of the 36 substations exceeded capacity by 2030 and 22 of 36 by 2050. Using DR, deferred reinforcement on 1 substation by 2030 and 0 by 2050. The reason that the deferral rate is higher in the early years is due to the higher level of forecasted EV and HP uptake by 2050. This would therefore trigger reinforcement even without SC demand. Having said that, it's extremely likely that the forecasted EV and HP uptake will change and evolve over the years. So for this reason, it's also beneficial to look at the level of demand exceedance. And this is the level of demand which exceeds the substation rating. As you can see from the bottom graph, in max cooling scenario, this shows a demand exceedance of 2.9 megawatts in 2030 and 15.2 megawatts by 2050. Applying DR produces a saving of 1.4 megawatts in 2030 and 3 megawatts in 2050. And for the 50% cooling scenario, the demand exceedance is 0.6 megawatts in 2030 and 9.5 megawatts in 2050. Applying DR produces a saving of 0.3 megawatts in 2030 and 1.4 megawatts in 2050. If we then scale that across ENW's network, this could defer 510 substation reinforcements by 2050 and produce a 1.4 gigawatt reduction in cooling load via DR. And just to add to that, we only scaled up across ground-mounted substations for this project, so those projected numbers would likely be higher with PMTs included. Next slide, please.
Brilliant, I can come in here. So we fed the network impacts that Del's just talked through into a high-level CPA, in which we annualized the required transformer reinforcements and the reinforcement costs, and compared those with the cost of procuring cooling DR to understand the potential benefits that DR could offer to the network. And the graph on this slide shows that cumulative benefit for two different DR options across those 36 distribution substations that Del just spoke to. And in this case, DR is applied for 2 hours coincident with the substation peak load. And the two options here, you can see they align with the DR scenarios that Del described on the previous slide. So 100% cooling with DR and 50% cooling with DR. And as you can see, both options defer more reinforcement in earlier years due to the reasons Del described previously. And just to note that if option 2 were to be scaled up across the entire ENW network, the cumulative benefit could be up to £38 million. And in a potential alpha, we would want to add more nuance to the assumptions in this CPA. Next slide, please. So while we were looking at cooling's potential network impact in the UK, we concurrently assessed existing cooling DR programs worldwide. We developed a framework for analysing them and extracted learnings that can be applied to the design of cooling DR programs in the UK. So the map on the left shows the spread of the programs we covered worldwide. As you'd expect, they're all pretty warm places, and the USA has the most advanced ecosystem of programs. So we bucketed learnings across 3 categories, as shown on the right. So with program design, we found that it really differs quite substantially across almost every program. There are a range of incentive mechanisms, event timings, notice periods, and so on. For the second one, providing optionality increases customer recruitment. So this is around things like level of control, eligible technologies, and the ability to opt in or out of events. And then finally, on customer preferences, well-designed programs give customers time to plan for DR events and may even action events without participants noticing, depending on the level of control available to the flexibility aggregator. And then beyond DR programs, we also looked at things like passive cooling, dynamic solar shading, and pre-cooling. And we found kind of how those could all complement or reduce the need for cooling DR. Next slide, please. So our analysis of those existing programs fed into the creation of 9 potential program designs for UK cooling DR. And we narrowed those down to the 5 you can see on this slide. So these are the 5 we deemed most suitable for kind of further feasibility studies and trials in future phases. So since cooling is more ubiquitous in commercial settings already at the moment, the first programs are likely to be best tailored to them. So that's the first 3. But then as residential cooling increases, programs designed for them will also become more necessary. Alongside this shortlist, we also identified key barriers to UK cooling DR and some recommendations to overcome them. These include a lack of knowledge on the willingness of UK residential and commercial customers to participate in cooling DR. Also the relationship between thermal comfort and building type and demographic differences sort of in the UK context. And then a final area where knowledge is lacking is around split system air conditioning DR. So split systems are likely to be common in UK residential homes compared to the more centralized AC systems that you see in places like the US, which have more established cooling DR programs. So these are all things we'd want to look at further. So if we go to the final slide, we've talked you through the discovery outputs, but I'll briefly summarize some key areas of focus for future work. So this includes more detailed network modeling, which accounts for things like distributed solar generation and a much wider spread of housing types across more substations. We also want to better understand consumers via market research into awareness of space cooling and the appetite for kind of flexing any cooling that they have. And then finally diving into that short list of 5 program designs and kind of really starting to gear up for a trial with flexibility aggregator involvement. think we'll leave it there. Thanks for listening, and yeah, welcome any questions.
Awesome, thanks everyone. And we're running slightly behind, so I think we'll leave the questions in the Q&A, but can I ask the project team to type up any responses? We've had a couple in the Q&A box, then also one in the chat as well, so those can be picked up. And we've also had one come in from OptiHeat after their presentation, so if they're still around, can they pick those up? Just for in the sake of time, we'll move on to the next one. So if I can ask HeatNet and the UK Power Networks team to come onto video and start the presentation.
Yeah, so good morning, everyone. So here we are to show and tell the success of our project, HeatNet. Next slide, please. So here I would like to introduce our team. So my name is Inam Shah. So I'm a project manager at UK Power Network. And we have two partners, Passive and IC Consultant. So Matt, Denny, Frederick, and Gore. Next slide, please. Over to Matt here.
Good morning. My name's Matt Osborne from Passive UK. We're a smart heat pump control provider. We've been working in this space for the past 10 years, and I lead on our innovation project. So thank you for the introduction, Inam. So what's the problem that we're trying to solve with HeatNet? Well, as the UK wants to hit its decarbonisation targets, we need to move away from using fossil fuels to heat our buildings. And heat pumps are well understood to be one of the core technologies to help achieve this, but they will have important impacts on local electricity networks. The UK's got very ambitious plans for driving up heat pump installation rates from around 35,000 now to up to 600,000 a year by 2028. For this amount of heat pumps will obviously have a huge impact on our power system, potentially doubling peak demands from a typical home from under 3 kilowatts to 7. Our networks were just not designed to cope with this, and the cost of upgrading them will ultimately be passed on to end consumers. The cost of these upgrades will vary, but estimates are around £20 billion from National Infrastructure Commission for distribution networks alone. Understanding and planning of how to deal with the impact of more and more heat pumps on the network is complicated. So the demands from heat pumps can vary a lot, varying within a day, throughout a year, and especially during worst case cold weather scenarios. Demand can also vary depending on house type, consumer type, and so on. For distribution networks, there's also other very important uncertainties, such as where will the heat pump load emerge on their network? How will the loads from multiple heat pumps interact with each other? And for this, location is really important. Where installations are near a substation, they present less of a challenge, but clusters of heat pumps at the end of low voltage feeder lines could result in higher voltage drops, and that then could trigger earlier reinforcement. Next slide, please. So we think HeatNet could provide a solution. So HeatNet is aiming to explore potential for an alternative service provision where providers are contracted to keep power demands from groups of heat pumps within pre-arranged capacity and voltage drop limits. Providers offer an end-to-end service to DNOs to help accelerate the electrification of heat and limit the cost of reinforcement. The HeatNet service could connect directly with DNO's digital planning and operational tools. Ultimately, through this project, we want to build a common method for this. This would need to cover all consumer protection arrangements as well as details around performance risks so that the DNO maintains its safety of its network. We hope that ultimately HeatNet could help install more heat pumps on the network, but using less expensive reinforcement and critically, without compromising consumer comfort. Next slide, please.
Thanks, Matt. So this is how we divided our work packages. So the work package one was the project management, And the work package 2 was the LV network interdependence. And the third was the household energy demand forecasting. And the fourth one was HeatNet scenario modeling. And the last one was the cost benefit analysis. Next slide, please. So how we actually manage our work packages. So we successfully signed the SIF collaboration agreement with all the parties, ensuring alignment and the commitment to our shared goals. Strong project governance was established, and we set up a shared area for documents and the communication, making collaboration seamless and efficient. So we kept the key documents like the PID, DPIA, risk register, project tracker, and lesson learned log up to date, which was crucial for monitoring progress and potential risks. Regular calls were held to review progress and address any key issues promptly. And I'm very proud to say that there were no significant changes to our project direction, allowing us to maintain focus and momentum. And all the work packages were completed on time and within the budget. Looking ahead, we need to process the final invoices and preparing for the alpha submission. Next slide, please. Handing over to Matt.
Thanks, Tinam. So I'm now going to take you through a process of the overview of the work packages that underpin the HeatNet optimization process. So the first and perhaps most important step is to generate a voltage drop matrix and a sample area of UK Power Networks LV network. So what does that mean? Well, the power drawn from each property on a network adds to the overall voltage drop across a network. So when one property draws power, this not only causes a voltage drop at that particular house, it also affects the voltage levels on all of the other properties that are connected to the same network. Using a matrix, we can understand how loads from one property impact the loads on others on the network. You can see a graphic that we generated on the right. Properties are numbered from both X and Y axes, all the properties on each one, and the impact of one home has on the surrounding network is a lighter color. As you can see, the properties in the far end of the network, represented in the bottom right-hand corner, have a larger impact on the surrounding homes. Now, the model that we built here was an early proof of concept, but we were able to check it that was reasonably accurate compared to power flow simulation used in UKPN's power network planning software. The aim is ultimately that we use this matrix to train our machine learning algorithms to help coordinate and manage loads from heat pumps on this particular network. Next slide, please. So now that we've got our matrix, the next step for us was to build accurate simulations for heat demand for homes on our subnetwork and then estimate the additional power demands from transitioning to heat pumps. We used these profiles to help forecast the effect of increasing number of heat pumps in our area. We used a range of sources, generated a number of archetypes of homes to cover all the homes within the area. We found that there was a large range of space heating demands based on building types, flats, houses, and so on, as well as occupancy patterns, families, couples, retired people, and so on. We used these models to generate half-hourly demand profiles for these homes based on them switching over to heat pumps. We then ran a series of simulations based on coldest year, worst case scenarios using local weather station data. And finally, we ran two sets of control systems, a standard thermostatically driven control system and passive machine learning optimized controls. And as you can see on the graphic at the bottom, user set points marked in the red squares were met in both, but the power load profiles, which are the sections in gray, were significantly flatter. That's a useful distinction, which we'll come on to next. So next slide, please. Final stage in our modeling piece was looking at scenario modeling. We wanted to understand how many heat pumps we could install on our sample network before we hit capacity limits or maximum voltage drops for any one home in that particular area. So to do this, we first produced our annual baseload using UKPN's own planning tools. That's the graphic in the center, the top. And then we mapped this back to our 20 households. Finally, we set a sequence of installing increasing numbers of heat pumps onto our network from 0 now up to 172 properties or 100%. And we found that if we distributed those heat pumps at random, we hit voltage drop statutory limits before we hit substation limits, particularly for this network. So we set about trying to calculate the best possible heat pump installation sequence to limit the impact of voltage drop in order to hit the capacity limits, because we hit the voltage drop first. So ultimately, what we found by a controlled sequence of installations to limit voltage drop before we hit the capacity limit, we found that if we combined passives demand flattening, so using our control technology, as well as our prototype HeatNet coordination algorithms, we could install about 30% more heat pumps using the same network infrastructure. So I will now hand over, yes, and crucially, the number of heat pumps we managed to install was not compromising any user comfort. So I will now pass on to my colleagues at Imperial who looked at the cost benefits of applying this new method. Next slide, please.
Thank you, Matt. So our assessment delved into the intricate system benefits and role of HeatNet, examining its impact on the entire energy system development and operations. We employed the integrated whole energy system model, which optimizes multi-energy infrastructure development and operation. We compared a system without HeatNet to one with the HeatNet solution, using the customer transformations, one of the future energy scenario from National Grid. So our analysis assumed that HeatNet would optimize the building fabric's thermal storage and enhance the heat pump COP by 15%. This would reduce electricity load and the peak, and thereby aiding in regulating network voltages and the flows. So the modeling results shown by the graph in the middle suggest that by 2050, HeatNet can reduce GB's energy system costs by 2.46 billion per year. This includes 584 million per year saving for the UK power network customers. 84 million per year savings come from the reduced distribution network reinforcement needed to accommodate load growth and electrification. The total GB's low voltage distribution capacity can be reduced from 95 gigawatt to 85 gigawatt as shown in the graph on the right. Broader system benefits include saving in the investment cost of low carbon power generation, heating system, and other flexibility technologies such as heat storage and electrolyzers. I hand it over back to Matt. Next slide, please.
Thank you, Danny. So what did we learn? Well, HeatNet Discovery explored how our smart controls can help install more heat pumps on a low voltage network without extra reinforcement by reshaping electricity demand and improving overall heat pump efficiency. We developed a proof of concept voltage drop matrix using UKPN's sub-network data. We modeled the electrical demand for installing increasing numbers of heat pumps onto that sample network and simulating power demands for every half hour over the year during a cold winter. And finally, we demonstrated a new way to increase heat pump penetration on that sample network within current design limits. And as Danny has shown us, the benefits of heat network could be significant. We looked at £2.5 billion a year, whole energy system benefits, and 500 million a year for UK power networks on their distribution network. So next slide, please. Just going to skip on this very quickly. We have an alpha phase planned where we're going to look at developing our modeling tools, as well as looking at the scenario modeling to be able to extract voltage drop data better from planning tools and explore how we can improve real-world planning scenarios and operational planning for within the low voltage network. We need to understand the business models that we could use within Heat Network, as well as regulatory and operational impacts. And finally, we'd like to look at whole system benefits of HeatNet under different future scenarios. Next slide, please. Any questions?
Yeah, thanks very much, team. I think we've got time for one question, and then we'll have our break before the last two presentations. So we've got one in the Q&A here. Given the wide range of heat pump makers and controllers, has the project looked at how the aggregation of enough heat pumps will be achieved, i.e. how do you ensure individual customers sign up to HeatNet?
Absolutely. I mean, we're trying to, first of all, look at, is this a proof of concept? Is this something that is even going to achieve any form of saving? That was our first ask. How we can then deliver it in terms of the different business models, integration with other heat pump manufacturers, other systems, that's something we need to dig into within the next phase and look at the different business models. At the moment, it was purely a proof of concept. Does this even achieve an outcome? Is it worth taking to to the next stage? So I'm sorry, that's a bit of a non-answer, but like I said, it's just trying to demonstrate the proof of concept to begin with.
Yeah, no problem. Thanks so much. I think we are not got enough time for any more, but if any more come through in the chat, if you can type up any answers, that would be much appreciated.
Yeah, I'll happily take that offline as well. If anyone wants to wish to contact us and reach out, we're happy to pick up any questions as well. Thank you.
Awesome. Thanks very much, team. And yes, as I mentioned, we are now going to have a short 10-minute break. So if I can ask for prompt return at 5 minutes past 12, in particular for the wastewater sourced heat project from UK Power Networks. And we will get started back at 5 past 12. So see you all then. Hello, everyone, and welcome back. Hope you had a good break. As I mentioned, we've got 2 more presentations left to go. So if I can have next slide, please. And if I can invite Ben and Alex from Project WASH to give us their 10-minute presentation. Over to you guys.
Yeah, thanks, Joe. Hi, everyone. We are Project WASH, which is a Ofgem project in collaboration with Guidehouse. I'm Ben Turner. I'm an innovation engineer at UK Power Networks. Alex, if you're on, I can't see you yet. Do you want to say hi?
Yeah, good afternoon, everyone. Alex Hoyle, also managing consultant from Guidehouse.
All right, next slide, please. So yeah, just to kick things off, you can go to the next slide, please. So the UK heating sector is going to decarbonise if we're going to meet net zero. And one of the ways of doing that is replacing your conventional gas boiler with air to source heat pumps or various other options that will require an electricity connection. So if everyone's going to do that, we're going to have more and more people connecting to the distribution network for an electricity connection, looking to connect their air source heat pump or various other heating methods. And essentially what that's going to do is just create a lot more strain on the electricity network as more and more people are looking to connect, which will lead to large peak electricity demand, larger connection capacity requests, and we'll kind of create strains on the network, which will require us to spend a lot of money trying to reinforce it. So improving the capacity just to be able to facilitate this transition to a low carbon source of heating. So there's various sort of projects that are going on that are looking at ways where we can minimize this electricity demand through looking at alternative heat sources. And the great thing about the rise in heat pumps is that you're now dealing with a slightly lower sort of temperature to be able to use to heat your home because they're more efficient than conventional gas boilers. So there are various options of low quality heat that you can potentially utilize. And this project is looking at wastewater heat. So through various studies, the project team have been looking at, okay, well, if we look at wastewater, sort of wastewater heat sources such as sewers or treatment plants, can you actually extract the heat from those different sort of utilities, and can you use that to essentially lessen the load on a heating network by transporting that heat to where you need it? Maybe preheating the feed to a district heating sort of network. And this will in turn reduce the electricity demand on the network. There's various benefits that we believe will come out of this. And that is all of the ones I sort of mentioned before, which is reduced electricity demand, reduced connection requests, and reduced network reinforcement costs. So that is how we see WASH playing out. Next slide, please. So the discovery phase so far, we've done various sort of different work packages. There was a pretty comprehensive literature review looking at other applications where this has been done across GB as well as internationally. And then what we did is set about mapping out all of the different wastewater sources across the UK, as well as mapping out prospective heat networks. Within reason, you can pump the waste heat from a wastewater source to a district heat network. So sort of overlapping those against one another allowed us to sort of look at the potential for where you could carry out this work. A series of assumptions were made, which Alex will get into, to sort of develop this a modeling sort of approach of the amount of heat that you could feasibly extract and what that would mean for heat pumps, and can you potentially downsize the heat pump to deliver the same amount of heat. And then we looked at developing a sort of commercial framework. Now there's so many different stakeholders that are going to be influenced by this project. Water companies, heat network operators, as well as DNOs like UK Power Networks. So developing a really robust commercial framework is super important for this. And then all of this work has sort of fed into an overall cost benefit analysis, which will sort of benefit all the different users that we've mentioned before and try and come up with something that works for everyone. So next slide, please. And over to you, Alex.
Yeah, thank you, Ben. So I'll just give you a run through of the outputs from each work package. So next slide, thank you. So work package 1 was a literature review. So we were looking at this from a technical, policy and commercial perspective. One of the key highlights from that literature review was identifying 14 large demonstrator sites. And actually, as a project progressed through stakeholder engagement, we did identify a few more. So these 14 sites really proved that this is a feasible solution and extracting wastewater heat from sewers for use in heat networks. Next slide, please. So next, we wanted to look at quantifying the potential for wastewater heat. So we looked at sewers and treatment plants, and this is our methodology for sewers. Now, unfortunately, getting sort of exact locations for sewers was challenging, so we sought an alternative approach, which we identified during the literature review. So we looked at areas where there was sort of a population equivalent of over 5,000, and in the literature review is identified that where you've got sort of a PE of 5,000, there'd be enough sewer flow to extract wastewater heat feasibly. So we use census data to look at 1 square kilometres where there was more than 5,000 residents and therefore sufficient PE. And then we made an assumption of a discharge of 200 litres per day per person to estimate the total recoverable heat from sewers, and we did that using the specific heat formula. And then we looked at sort of limitations of the methodology and drew some conclusions. And we identified that 6.35 terawatt hours of heat could feasibly be recovered from GB sewers every year, and that's the equivalent of just over 500,000 homes. Next slide, please. So we also looked at wastewater treatment plants. So fortunately, we're able to access some locational data for wastewater treatment plants, and you can see those plotted out on the right-hand side. Now, in our literature review, is identified that heat could be pumped up to 2 kilometres. So we were looking for heat networks on areas with sufficient population density in close proximity to those wastewater treatment plants, and that was a site that was a site that was considered feasible to extract wastewater heat. Now, we use the DESNZ heat network planning database to identify the locations of heat networks. Now, we know that is not exhaustive, so this is likely an underestimate. So using all those identified sites, we used a specific heat formula, again, to calculate the maximum possible heat that could be extracted, and we calculated that 20 terawatt hours of heat could feasibly be recovered from treatment plants every year, and that's equivalent to about 1.7 million homes. Next slide, please. So here, just summarising sort of a GB-wide view. So the wastewater heat network overall could sort of carries approximately 101 terawatt hours of heat. Now, we know that can't all be extracted, and we're then considering the current heat networks meet 3% of UK demand, and 40% of these use heat pump as a fuel. Theoretically, at the moment, wastewater heat could meet all that heating demand. And now we know that the government's got ambitions to grow this, so looking for heat networks to provide up to 80 terawatt hours a year of heating in the UK, and 85% of those would be powered by heat pumps, which means 68 terawatt hours a year of heat from heat networks in 2050 will require electricity as a fuel. So from our calculations, we think wastewater source heat could meet 38% of that demand, and due to the coefficient of performance, it could reduce the impact on the electricity network by 50%. Next slide, please. So we looked at possible business models and commercial frameworks to implement WASH as a solution. So we considered 4 solutions. So water and sewage companies commoditize heat as a product. So they sort of build the infrastructure and sell the heat. A capex sharing between water and sewage companies and local authorities and HNOs to build the infrastructure together. A land lease agreement between water utility at a treatment plant, so the HNO can sort of build the infrastructure, and then joint ownership of wastewater assets between water utilities and HNOs. And then we then assess those on the 5 criteria on the left-hand side. to assess which will be most feasible. The first 3 look really promising. The 4 is unlikely to happen. Just joint ownership between wastewater assets and a HNO would be challenging. Next slide, please. Sorry, I'm moving through these quite quickly. So finally, there was a cost benefit analysis. So we considered 5 benefit streams, which was a financial benefit due to avoided reinforcement cost, financial benefit due to lower CO2 emissions, reduced electricity costs achieved through reduced electricity usage, reduced capex achieved through heat pump downsizing, and the final benefit due to lower CO2 emissions. So here we've summarised the benefits. So GB wide, there's over £5.7 billion worth of benefits by 2050, and 3.3 million of that being, sorry, 3.3 billion of that being within the UKPN licence area. Looking at the deferred reinforcement savings, so 155 million GB wide and 91 million of that in the UKPN licence area. And then looking at just under 800 kiloton equivalent CO2 savings GB wide, and about half of that being in the UKPN licence area. So as you can see, this solution has potential for real benefit for the GB energy consumers. And Ben, I'll pass it back to you to wrap up. Thank you.
Yeah, however long we've got left. But yeah, the plan for sort of the next stage of this project is to really build on some of the learnings that we've developed at Discovery, working closely with various water companies as well as heat network operators to kind of refine the sort of data that we've gathered already. And then we're looking to build a sort of digital solution where a heat network operator, a water utility, or another distribution network operator could actually use this tool to understand the headroom at different substations and how wastewater heat can be used to actually help you install a new district heat network, by understanding, how you could maybe reduce the electricity requirement of your new development by utilizing wastewater heat. And we see that as a really beneficial sort of digital tool to help this sort of whole system approach. But yeah, thanks very much, and happy to take any questions.
Awesome. We've had a couple in the chat come through. I think one's being typed as a response at the minute around engaging with heat networks. And if you've done any so far with the project, you talked about it as a in scope for alpha. But I don't know if you want to touch upon that one. Did the project engage with any heat networks in the UK, e.g. Bristol or Exeter, to see whether wastewater heat has been considered already in their models?
So we didn't talk to Bristol and Exeter specifically, but we spoke to a couple in Scotland. We are engaging with heat network operators, and then we spoke to some of the schemes we identified in the literature review in Europe. So yes.
Awesome. And then there's a one on the reference of 200 litres per person per day that you might want to pick up in the text. I don't know if you want to.
I'm struggling to see the ones in the. Okay. 125 litres per hour per day. That sounds quite high, but something we'll sort of consider in our alpha stage. Yeah.
So I can't see any other ones in the chat. I'll just check Q&A.
Yeah, there's one from Jenny at 1216.
Yeah, wastewater and water companies use a large amount of energy to treat the wastewater themselves. So have you compared the cost savings between using the waste heat for heat networks versus using the waste heat to reduce the energy demand at the treatment sites, which presumably impact the energy networks too?
Yeah, so that we're aware the water companies are looking at this themselves. So there's an Ofwat project at the moment looking at that. But if you think that the sewers are sort of the end of the line, so they could take the heat out of the effluent as well and use that. But a lot of these applications, if the sewer's sort of in a city near the demand centre, it'd be more useful for heating district heat networks rather than the treatment plants.
Yes, there's another project, isn't there, running that is actually some water companies are looking at offsetting their own demand by using their wastewater heat, but this is more of a commercial framework that will affect maybe more directly affect energy consumers.
Awesome. And Carter's put another comment in around clarifying that 125 number, and it being per litres per head per day.
Sorry. The literature review I didn't said 200, so maybe we have got a slight overestimate on that, but some of the others were an underestimate. So again, something in Alpha we would look to redo those sort of calculations and make sure they're still correct. So thank you for that.
Awesome. I think that draws us to end of this one. If the audience does have any other further questions, do put them in the Q&A and we'll look to follow up either through text type afterwards or after the call. So do fire away. But last but not least, we've got project 3, so fuel cell renewable energy equity, led by Northern Powergrid. So if I can ask Northern Powergrid and the rest of the team to turn cameras on and walk us through their presentation.
Hello, everybody. Hopefully you can hear and see me.
All good.
Good, excellent. My name's Emma Burton and I'm one of the innovation project managers at Northern Powergrid. So the 3 projects that's been delivered in partnership with LCP Delta and EA Technology. The overarching aim of this discovery phase is to take an initial look into the development of a commercially viable technology solution which can help drive us towards a more resilient energy system, and one that isn't dependent on a sole energy vector. I'm going to hand you over to Johnny Buzzing from LCP, who is going to take you through the findings of the discovery phase and outline our future plans for the Alpha.
Thank you, Emma. Yes, so as Emma said, I think that the key challenge that we were looking at really with this project is how we maintain resilience in a kind of fully electrified system. And I think, there's lots of examples of how kind of behind the meter assets and demand side flexibility and hybrid systems have been used in the past to provide system resilience. But I think, in some cases they are limited in terms of a few factors. So an example of battery storage, obviously that only gives you a limited amount of resilience. It doesn't provide it, on a sustained basis. If we're thinking about different hybrid systems, there's naturally the question around, well, how low carbon is that fuel source that's being used to power dispatchable generation to provide you with that hybrid solution and sustained resilience. And then there's also the issue potentially around low carbon. So are they actually compatible with our low carbon agenda? And what our solution builds upon really is thinking about, well, what if we integrate fuel cell technology as a dispatchable technology that can be integrated within a microgrid and can be used in support with behind the meter assets and a centralized BESS system as well to provide that longer term sustainability resilience to the system. Our project was consisted of 3 core work packages. So first of all, we had a technical work package, and this was testing the technical feasibility of the concept that we put together. So there were a number of different kind of tasks that we performed. We did a couple of literature reviews. So the first literature review was looking at any barriers to the deployment of our solution, so regulatory, policy, and legislation as well. We also did a literature review looking at other resilience projects and fuel cell CHP projects that are that have been adopted across the world. Project partners EA Technology also conducted a network modeling piece, so looking at the technical potential for our solution and the extent to which it can be deployed to sustain a network, and then also kind of following those pieces of work, we also came up with 3 kind of configurations or 3 use cases for our solution. We also conducted economic analysis. So this was high-level cost-benefit analysis that highlighted some of the customer and also system costs and benefits. And we also engaged with stakeholders as well. So there was a task of identifying the key stakeholder groups and then engaging them through a series of bilateral conversations and also a workshop that was held earlier in the month of May. Next slide, please. Okay, so just to quickly go through the three configurations or use cases that I mentioned. So our first two configurations are based on deployment of our concept in a new build housing development. So use case 1A on the left-hand side there looks at a solution whereby you have individual micro CHP fuel cells installed in households and supporting the households themselves, but also potentially the wider housing development, so apartment blocks which are fitted with exhaust air heat pumps. We then have use case 1B, which is looking at a centralized solution. So a larger fuel cell micro CHP is installed potentially kind of within an apartment block, and that communal CHP is used to provide heat and power to the apartments themselves, but also potentially the neighboring individual households as well. Next slide, please. We also looked at a retrofit solution as well. So getting away from the new build deployment, but looking at how this could actually exist in an existing substation circuit. So this is very similar to a previous project that LCP Delta and Northern Powergrid were involved with called Resilient Customer Response. That project looked at the potential for just behind the meter assets to provide a resilient system. And as I said earlier, what we're doing here is evolving that and integrating fuel cell micro CHP to provide that sustained resilience. And in this example here, as you can see, we've considered the inclusion of individual micro fuel cell CHPs in households themselves. Next slide, please. In terms of what we've learned from this project, just to go through the three work packages again. So on the technical side of things, as I've just kind of walked you through very quickly, we identified three configurations of the concept that could be integrated in a new build housing estate or existing energy network. These were kind of developed throughout the project based upon the findings from each three of these work packages. In terms of the literature review that we did, which looked at existing projects or demonstrations, we did identify a number of different demonstration projects that had demonstrated the potential for components of our solution, and in one case was a very close match to the actual solution that we came up with as well. That was something that was deployed in Japan. So there was lots of kind of useful learnings that we took from those projects to integrate into ours. In terms of the network modeling, as I mentioned, this was carried out by EA Technology. This was a real kind of critical piece of the analysis, and it really kind of highlighted the need for that centralized battery energy storage system to help support this concept to be effective, showing that kind of micro fuel cell CHP on its own isn't enough to provide that system resilience. You really require that support from wider assets as well. And then finally, as well, we had the literature review, which looked at the legal, regulatory, and commercial barriers. In terms of the economic analysis, as I mentioned, we did conduct a cost-benefit analysis to test the different test the different use cases. The highlights from this CBA showed that the collective usage of a fuel cell found to result in system savings of 8% relative to a counterfactual. So that corresponds to use case 1B that I showed in the previous slide, where you have a communal, slightly larger CHP situated in an apartment block, which is supporting the apartments as well as the wider housing community. At this stage, given the current kind of market dynamics, the deployment of individual micro fuel cell CHPs was not found to be cost effective, and that's largely due to the very high capital cost of micro fuel cell CHP at the moment relative to heat pumps. What we also found was that system savings could be considerably higher for areas with greater energy security challenges. So we looked at a sensitivity where we changed the values around the amount of network disruption and the frequency of network disruption, and we found that that led to higher benefits. And we also explored at a very high level the potential business models that could be used to deploy this solution. So concluding that energy sharing business models would be required. In terms of the stakeholder engagement, as I say, this involved, first of all, kind of identifying the key stakeholders that would be involved to kind of implement this concept and have it operational as well. And then we engage with them, as I say, through a combination of a workshop and also some bilateral conversations. We got some really useful insights from the different stakeholder groups. So we discussed with fuel cell manufacturers, and that was mainly to test our technical assumptions that we've made, but also check our alignment with the kind of the fuel cells that we had used in our modelling, and also and that we proposed for this concept, and also with their current product range. Housing developers, I kind of really emphasise that importance around getting customer acceptance. And finally, energy suppliers as well had some really useful feedback on how we could develop the business model further by incorporating different revenue streams, such as those providing that you could get from providing system flexibility. Next slide, please. In terms of how we want to take this forward further, I think on the technical side of things, there is definitely, we want to explore the communal solution in more detail. So potentially doing hardware in the loop testing to understand concept performance and compatibility next to other assets. On the economic side of things, as I say, one of the key piece of feedback from that we got from energy suppliers was around how we could develop the business model further. So that's something that we'd want to explore with them in a bit more detail, looking at potential flexibility benefits in particular. I think there's also kind of additional steps that we could take to further refine our economic analysis. So more granular microgrid modelling, I think, would be very beneficial to this study. And also further collaboration to refine our assumptions with other groups of stakeholders. And finally, further engagement with policymakers and also the ENA as well, to just make sure we have alignment with, as I've put there, the role of gas networks and technical standards going forward, but also the wider kind of UK policy direction as well on hydrogen. Thank you. That's the end of our slide pack. Happy to take any questions.
Yeah, thanks so much. We've had a couple come through in the chat. So the first one, could you please go over the differences between use case 1, new build, versus the retrofit model for existing houses? Will they use the same type of micro fuel cell CHP?
So yes, the idea would be they'd be using the same technology. I suppose one of the main differences between 1A and the new build solution and the retrofit would be around the energy efficiency of the home. So in our modelling, we've assumed very high standards of energy efficiency in the new build situation, where we know that wouldn't necessarily be the case in the retrofit solution. So yeah, potentially a more difficult I guess archetype or more difficult kind of use case there to prove the cost benefit analysis of.
Awesome, thanks very much. And then sort of in a similar vein, second question, what is the counterfactual you were comparing against when you mentioned the 8% and the 35% system improvement of the fuel cells burning methane?
Sorry, I just missed that last bit, but it's
are the fuel cells burning methane as the second part of the question?
in all case studies, the fuel cells are burning natural gas. The counterfactual is that rather than using fuel cell CHP, they are using heat pumps. But yeah, we've used slightly different counterfactuals for each of the different use cases. So yeah, happy to provide more detail on that if you need it.
Yeah, if you can maybe put a typed response to that one in the chat.
Yeah, sure.
How I'd best get in touch with the team, that would be good. Let me check to see if any others come through. I can't see any other ones in the Q&A or the chat, and that pretty much brings us up to time. So thanks so much to all the projects. If I could have the next slide, please, that would be great. Let me close the Q&A tab. Yeah, so that wraps it up for our 5 presentations from our projects for this session. But as you can see from the slides here, we have quite a few other show and tell sessions coming up throughout the rest of this week. There's 5 other sessions, 1 more today, and then 2 tomorrow and 2 on Wednesday. please do register for them, that you wish to attend. Registration links at the top of the slide, and we'll also be adding it to the chat shortly for you to access those. And next slide, please. Yeah, if you'd like to find anything more about the Strategic Innovation Fund, there's a myriad of ways you can connect with us, and these are all set out in the slides. Our best place is the signing up for our newsletter. The second point there, where you can get regular updates on what's happening with the SIF. But as I mentioned, this is part of a series of show and tells, which will be going up on YouTube in the next couple of weeks as recorded sessions. We also have our previous rounds and phases show and tells up there as well, if you want to learn about what previous rounds and projects have been up to. We have a podcast series, which has just had a few new episodes released, which you can listen to, and also our other YouTube playlist. And if you have any inquiries about the SIF, do reach out to us on our dedicated mailbox, sif_ofgem@iuk.ukri.org, and we'll pick up any questions there. And I think with that, we come to a close. So I'll make sure that the link has been put into the chat for the other Discovery show and tells. Do sign up to those if they're of interest, and thank you very much for everyone for attending and for all of the 5 projects that came and talked about what they were up to. Thanks so much for attending, for those that asked questions, and I hope you have a good rest of the day and see you around at some more of our show and tells.